Reflow, Group 45, by Bartek McCormick, Timothy Lynch, and Andrew Coville. Media choices. Our choices for media range from pebbles to activated charcoal to ground glass. Our team's primary design goals for this project were simplicity, flow rate, and dye removal while trying to optimize cost. We chose to use activated charcoal due to its extremely high degree of microporosity, giving just 1 gram a surface area in excess of 500 meters squared. We thought that this would most effectively aid our team's design goals.
Our first design consisted of 17 grams of charcoal in a 1x6 inch tube with a 1-inch end cap at the bottom of it that has a hole drilled into it to allow filtered water to escape, and a cheesecloth separating the activated carbon from the 1-inch end cap. While the results of our first design were really good, the concentration of the dye was increased during the third design day. Nonetheless, the results are as follows, with an average flow rate of 0.625 milliliters per second. Our second design involved increasing the amount of activated carbon to 30 grams. The rest of the design remained the same. We see that the flow rate is marginally slower than that of 17 grams, our first design, with an average flow rate of 0.605 milliliters per second. Also, the dye removal didn't appear considerably cleaner. The higher cost and no real benefit were able to disregard this design. Our third design is as follows: 17 grams of activated charcoal with 8.5 grams of small glass beads. We thought that the glass would decrease porosity, therefore giving more time for the dye to be removed by the activated carbon. The results of our third design are as follows, with an average flow rate of 0.417 milliliters per second, considerably slower than the previous 2 iterations. For our final design, we chose 17 grams of activated charcoal, which happened to be the original amount, seeing that no following iteration improved dye removal significantly. Also, through testing, we found that the added cheesecloth, which was a 8x6 inch ball of cheesecloth below the activated carbon, increased flow rate without a major influence on dye removal. With time to spare, we decided to add some elegant decorations featuring the Reflow mascot, which promotes water recycling through a friendly image. Final design results are as follows. We have an average flow rate of 1.33 milliliters per second, which is over double the flow rate of our original design. We also were able to finish our spectrophotometer by this point of the project and get an average reading of absorbance of 0.24.
On the left, you see a circuit diagram of the spectrophotometer, and on the right is a picture of the real photometer. This photometer was used to make a calibration curve, shown next. We used our spectrophotometer to get this calibration curve. Using our final filter design, our spectrophotometer showed that 32.8% of the dye was removed, an average absorbance of 0.24. Obviously, the professional photometer outperformed our Arduino photometer. However, considering our photometer was about 1/100th the cost of the professional one, ours did just fine.
The cost breakdown is broken into 3 sections. The first being what actually played a role in filtering the dye, the second being what materials we used for decoration, and the third being what we bought using real money from McMaster-Carr, with our final cost shown below as well, which ended up being $122.5. In conclusion, our team worked very effectively throughout the project. We were able to change direction from focusing on dye removal to mainly flow rate in order to remain competitive in the competition. Given more time to work on the filtration project, we would have tested each iteration with the spectrophotometer to get an actual reading of absorbance for each. The photometer was only ready for our final design. We also would try more varied designs to seek better dye removal.